Hello everybody, welcome back to Calculus 3 Online at Frederick Community College. In this video, we begin discussing multiple integration, which is chapter 5, and in particular, we will discuss the first section, which is double integrals over rectangular regions. For this lecture, we have two main objectives. First, we will discuss double integrals in terms of a Riemann sum. So there will be a little bit of a review from Calculus 1. And then most of the lecture, we will focus on computing double integrals over rectangular regions. So let's go ahead and derive this notion of a double integral. First thing we're going to do is have a quick review of Calculus 1. At the very end of that class, once we learn how to compute derivatives and antiderivatives, we also looked at a graph of a function. So for example, here we have a function y is equal to f of x, looks like a polynomial function. And we said, how can we compute the area under the curve of this function if we restrict our domain, right? So we have R as the domain for this polynomial function, and we said let's restrict it to something like from A to B, okay? And if we were to compute the area under the curve, one way we could do that is split up our interval AB into finitely many subintervals. In this case, looks like we have 8, so we say n will be 8, okay, 8 subintervals of equal length. And then we know what this length is, and we can pick a point. It could be left point, right point, middle point, or just any random point. So in this case, this picture looks like we're using right point. Compute the value of our function of each of these right points, right? Okay, so over here. And then we know what this is. This is going to be f of x1. And if we multiply delta x, that would be our width of this rectangle, or the base of it, by the height, which is f of x, then we get the area of this rectangle right here. So of course, if we do for all of them, in this case we have 8, so we do this 8 times. We compute 8 areas of these rectangles, sum them up, and we get an approximation of the area under the curve. So that's what we've done in Calculus 1. And then we said, okay, well, how about we increase that number, not just 8 rectangles, let's say 20, and then 30, and then 100. And every time we do this computation, we realize that our area gets better and better. The approximation gets closer and closer to the true area under the curve. And that was the whole notion of an integral, right? So here's your definition from Calculus 1. We say that the area under the curve of a function on an interval from A to B is given by the limit, right? So we have a limit as n goes to infinity. So we have more and more rectangles. Summation, right? So this is us summing up the areas of those rectangles. And this expression right here is nothing other than height times width, right? So where delta x is just the width or the length of the base of each rectangle. And of course, as n goes to infinity, this gets really, really small, and we get the true area under the curve. Okay, so that's how we develop that whole notion of an integral. All right, now we're going to extend this idea to R3. Okay, so now here we are in R3. Okay, let's go ahead and make analogy with each of the components, right? So our function y is equal to f of x. Okay, now we have a function z is equal to a function of two variables, right? So x and y are the two independent variables. Okay, now our restricted region will be a portion of R2, right? So R2, that's your x, y plane. Okay, that's going to be our domain. And if we're restricting our domain to a region, right? So that's going to be this rectangle right here represented by R. And now let's discuss this. Amount of space that's under this surface over this region R, right? So how much space is taken? This is volume, right? Okay, it was area in our lower dimensional space, but now we're in R3. So the amount of space taken by the surface under the surface and over this restricted region, okay? That's what we would like to compute. So now we can do a very similar development of a Riemann sum, except in this case, we're splitting our rectangle R into smaller rectangles, okay? So we're splitting them with some width relative to X and then some width relative to Y, okay? And we can compute the area of this one rectangle right here. So what would that be? That would be delta X times delta Y, okay? And then if we multiply this quantity by the height, okay, which will be what? It will be just the value of the function at that point. If we pick a random point that belongs to this rectangle here, okay. Again, it could be one of the corner points. It could be just some point right in the middle or any random point that belongs to this small rectangle. Then we get the volume, right? So if we do F of that point right here, whatever that point might be. Now this is height times width times length. This is the volume of one prism, okay? And we can compute this volume for every one of these prisms. Add them up, and we get an approximation of the volume that's taken by this surface. So under the graph of the surface, under the graph, right, over this restricted region. All right, so that is the intuitive notion of Riemann sum. And if you want to see, a little bit more rigorous, a little more detailed explanation, you can refer to the textbook. But I just wanted you to see graphical representation of what a Riemann sum for functions of two variables looks like. So what is it? Now we say V stands for volume, is the limit of the double sum, because we need to sum up in one direction, so in the X direction, and also we need to sum up in the Y direction. Okay, so M and N, M would be the number of rectangles if we count it on the Y-axis, right? And N is on the X-axis. Okay, so what happens here? Both of these numbers need to go to infinity. So these rectangles, the little rectangles in R, get smaller and smaller. Okay, and this delta A, that just represents the change in the area of each one of these rectangles. So that's your delta A right here. Okay, so that is your area times the height over here, and we sum this up across X and across Y. All right, and that is the double integral. Okay, you can see the analogy between the two formulas for the area where we were working with a function of one variable. And now here's your actual definition. The double integral of the function f of x, y, what is it? Okay, so what is it? So we need to know what the restriction is. So R stands for region. Okay, sometimes it's a rectangle. And in this particular lecture, it's always going to be a rectangle, right? And in the next few lectures, we're going to take a look at different scenarios where R doesn't have to be a rectangle. Okay, so what is it? It is the limit of this double sum of f of x, y times delta A. Okay, that's the formal definition. That's all I wanted you to see as far as the definition and this whole notion of a Riemann sum is. Okay, so for the rest of the lecture, what we're going to do, we're just going to focus on computing double integrals. There's one more thing that I'd like to do before jumping into computational problems, and that's to discuss some properties of double integrals. So first, we have that the sum of two functions, if it's integrable, then we can split up the integral into a sum. So this one right here says if we have a sum in the integrand, then we can split this up into two integrals and add them up. Then the second function, the second property says that if c is a constant and we're integrating c times f, then we can take this constant up front. So we've done that for single integrals, right, where we integrated function of one variable. This is still true for multiple integration. Okay, the third one says that if R, the region of integration, is a union of two other regions such that they do not overlap. So this statement right here says their intersection is empty, except maybe an overlap on the boundaries. Okay, so that is okay. Then we can split this integral. Notice here the area that we're integrating over is R, and now we're splitting this into a sum of two integrals where we're integrating over S and then over T. Okay, the next property says that if f is greater than or equal to g on the entire region R, then so is the integral. Okay, and the fifth property says that if our function is bounded, so the underlying function that we're integrating is bounded by these two values. So let's say little m represents the lower bound, and then capital M represents the upper bound. So let me write it right here. This is lower, this is upper. Then the integral of this function is also bounded. And what is it bounded by? So this is little m times the area of the region. That's the lower bound. Okay, that's our new lower bound for the integral. And then upper bound would be the area of that same region times the upper bound m. Okay, so that would be the upper bound for the integral. In this class, I don't think we will use this rule too much. I haven't seen many problems that applied, but I think it's a good idea to at least see it once. Okay, the last property is the one that I really wanted to discuss. Okay, I think this one is useful. Okay, and this one we will be able to apply. So here we have the following. We have a function f of x, y, and then if we can factor it as a product, right? So if we can factor this as a product of two functions where we separate the variables and we only have a function g that's only in terms of x and then function h only in terms of y, then we can split this integral right here into a product of two integrals. Okay, but notice that the limits must follow, right? So the limits for x follow this integral right here. The limits for y follow this integral right here. Okay, so we will actually apply this rule to one of the problems in this lecture. Okay, now we're ready to tackle some problems. And the first example says evaluate the integral from 1 to 4 and then from 0 to 4 of the function square root of xy dx dy. So before we get into the computational portion of the solution, let's discuss what's going on here. What is it that we're integrating? We're integrating the function square root of xy. This is what is sketched. So I'll use GeoGebra to graph this function. You can see the image here, okay? What do these limits mean? So the inner integral, the one from 0 to 4, that is for x, right? So that's in the direction of x. Those are limits for x, okay? And then from 1 to 4, that's the outer integral, and that's for y. And the first thing that I always do, even when the problem is not asking me to do that, make a sketch of the region of integration. Okay, so what is the region of integration? It is a rectangle My x goes from 0 to 4. My y goes from 1 to 4. So it's a rectangle that sits in that portion of the domain. And let me kind of make a sketch over here. Where would that be? That would be somewhere here. Okay, so that would be the visualization that you can refer to. So this is my R. Now it's in 3 space, right? So we would like to determine the volume of what? The surface, and the surface, you can see the graph here, that sits over that portion. Okay, so that's what that R looks like. All right, so it's a double integral over a rectangular region. How do we do it? Okay, so what I usually do as I learn a new concept, I kind of split it up into parts. Okay, and I encourage you to do the same as you're learning how to do multiple integration. So what do I mean by that? I'm going to compute the inner and outer integrals separately. Okay, so here's my inner integral. All right, so I'm integrating from 0 to 4. This is square root of xy dx. Okay, so I just took the middle portion, the inner portion of my integral, and that's what I'm going to do. Now, how do we do this? Okay, so we remember, just like when we were computing partial derivatives, y, anything that has y in it is a constant. Okay, we're integrating with respect to x, so y acts as a constant. And now we're just working with an integral in terms of one variable. We know how to do that from calculus 1 and calculus 2. So I'm going to pull out y to 1/2, and that's my constant. And now I can find the antiderivative of x to 1/2. That's very straightforward. So that is the expression here. And now we evaluate it from 0 to 4. Okay, so I combine my constants over here. It's 2/3 y to the power 1 over 2. I evaluate this expression right here for x, okay, and what we get as the result is an expression in terms of y. So we have 16 over 3 times y to the 1/2. Okay, notice since we integrated with respect to x, once we do this, the answer over here should have no x. We integrated that variable out. Okay, there is no x here. Okay, that's one of the things that we should keep in mind as we go through this process. So that is the expression that we have left. And now the outer integral, that's just going to be a simple integral with respect to one variable, right? So we plug that back in. Okay, we have an integral from 1 to 4, 16 over 3 y to the power 1/2 dy. Notice this, all that matches. Okay, dy. Okay, that's good. And we have an expression in terms of y. All right, so we know how to integrate this. This is the antiderivative of our function. Okay, we combine our constants, carefully evaluate this antiderivative from 1 to 4. Okay, and then the answer is this value right here, 224 over 3. What is this? This is cubic units, okay, and that would represent the volume that is under the surface here over this region of integration. So this is my R, okay? All right, so what I would like for you to do, okay, as a little challenge, it's not really challenging, but I would like for you to pause this video and then swap the limits and the order of integration. So what do I mean by that? Instead of doing this, do the following. So do the double integral, same function, right? So it's going to be the same function, and now we're going to do dy first and then dx second. And of course, we have to swap the limits, right? So what were the limits for y? The limits for y were from 1 to 4, and then the limits for x were from 0 to 4. Okay? So why don't you do that before jumping into the next example? And spoiler alert, you should get exactly the same answer. Let's take a look at the next example. Here we would like to evaluate the integral x cosine xy, that's the function. The order of integration is dy dx, and we have a region where y is between 0 and 1, and x is between 0 and pi over 2. So this is another rectangle. And that's the first thing I'm going to do is graph the region of integration. Okay. And here they are telling us the order of integration. They say go in the y direction first and then in the x direction second. All right. So what do we need to do? I'm going to compute my inner integral first. Okay, so that's with respect to y, right? So we're integrating in the y direction first. We go from 0 to 1. The integrand is x cosine xy, and we're integrating with respect to y. Okay, so I'm looking at my function, and how did I find this antiderivative? Well, I have cosine. I know the antiderivative of cosine, that would be sine. Now, inside the argument, I have this expression x, y, and I know that if I were to differentiate with respect to y, by chain rule, I would have x, right? So that is exactly what happens here. So the antiderivative of my function is sine of xy. Okay, and you can follow u substitution to get to the same conclusion. But for me, when I look at functions, I'm trying to undo the process of differentiation. So that logic works better for me personally. So sine of xy, that is what our antiderivative is. And now we're plugging 0 and 1 for y, right? So this is y and this is also y. So once we plug this in, we get sine of x minus sine of 0, and of course sine of 0 is just 0. Okay, so notice we integrated with respect to y, and what we've gotten is the function of x. There's no y here. Okay, we integrated that variable out. All right, so then the outer integral, now we have sine of x. The integral is from 0 to pi over 2. We're integrating in the x direction. Okay, so that's an easy integral. We know exactly how to compute it. The antiderivative is negative cosine of x. From 0 to pi over 2, carefully evaluate it, and we get a nice answer. So 1 cubic unit would be the volume under this function right here, and I graphed it, and it is not a pretty function. It was not easy to get the right window to have a good looking image, so that's why I did not include it in the solution. But you can use GeoGebra and graph it, see what that looks like. Okay, so that is 1 cubic unit under this function over this region R right here. Okay, now what would we have to do if the order was switched? So I'm raising this question right here. If it was saying the integral and the inner integral is from 0 to pi over 2, and we're differentiating with respect to x first, right? So what will we do here? If we were to differentiate it with respect to x, it wouldn't have been as simple or as straightforward. And what you would have to do is apply differentiation, integration by parts. So that would be the rule that you would have to apply for the inner integral. So the point of this problem is that, yes, while you can switch the order of integration, okay, for double integrals where we evaluate them over rectangular regions, right? So this is, the emphasis is rectangular. Yes, we can switch the order and just swap the limits, but one way might be slightly easier than the other. So it's a good idea to really take a careful look at the function before we choose the order of integration. Okay, so if you'd like another challenge, you can attempt this problem right here, right, as is. So now you would be integrating with respect to x first, and then with y second. And of course, as always in mathematics, if you do one problem with two different methods, we should get the same answer. So you know that you should get one. Okay, but I wanted to bring your attention to an example where the order is important if you're looking at the difficulty of computations, right? Okay, of course we can do it either way. All right, so that's your example number 2. Let's take a look at another example. So here we have a double integral of the function x, y sine of x squared, okay, over the region R, where y is between 0 and 1, and x is between 0 and square root of pi. Okay, so here is my picture representing the region of integration. And in this case, we just have dA, all right? So they do not suggest either order of integration. So that is for us to decide which way we're going to integrate. Okay, let's see. I'm looking at this and I see that I have a function of x times function of y. So this is a good indicator that is going to tell you it doesn't really matter which order you're going to use. So I'm going to integrate with respect to y first. So I'm going in this direction. Okay, so the integral from 0 to 1 of the following expression, x y sine x squared dy. Okay, now x is acting as a constant, right? So this is a constant, so is this. So I can pull it out, all right? And then the antiderivative of y, that would be just 1/2 y squared, okay? And now I'm plugging in 0 and 1 for y. So it's important to emphasize that we're plugging this for y. Okay, so we do this carefully. Okay, we get 1/2 x times sine of x squared. Okay, again, this is where you pause and say, what did I get? What kind of expression did I get? Okay, we have an expression in terms of x only. There's no y here. Okay, that variable is gone. All right, so then the next one would be outer integral. Now we go from 0 to square root of pi over 2, and now we only have one variable, 1/2 x sine x squared dx. Okay, you can apply u substitution here and see that the antiderivative would be -1/4 cosine of x squared. Okay, I'm going to let you verify with u substitution that that is the antiderivative, and we evaluate this from 0 to square root of pi over 2. So this we plug in for x. Okay, so this is x and this is also x. We get a nice number, right? So -1/4 times cosine of pi, which is cosine of pi over 2, which is 0, and then cosine of 0, which is 1. So negative and negative will give us a positive. So the answer is 1/4. Okay, this is cubic units, whatever that might be, and that represents the volume that is taken by the surface over this region R right here. Okay, now at the very beginning of this solution, I've mentioned that I look at the function and I see a product, right? I see a product of two functions. So one challenge here that I would like for you to attempt is this. Let's split this integral into a product. So what would that be? So the first one is x sine of x squared dx. Okay, that would be everything in terms of x, and of course my x goes from where? From 0 to square root of pi over 2. Okay, and then we're going to multiply it by the integral for y, so that would be from 0 to 1, okay, of y dy. So this is your example of a double integral that we can just split into the product of two simple integrals, right? Why is that? okay, because the integrand function, right, the original function that we're integrating can be split into a product of those. All right, it's not difficult to see that we're going to get exactly the same answer. Let's take a look at our last example for today's lecture. Here we have a double integral of the following function, 1 over x plus 1 times y plus 1. And we're integrating over the rectangular region R, where y is between 0 and 6 and x is between 0 and 1. So first I am making a picture of my region of integration. Okay, and here we notice right away that our integrand, the function inside the integral, can be split into a product of two functions. One function in terms of x only, the second function in terms of y only. It's pretty clear. So we're going to apply that rule. I believe it was rule number 6 that we've discussed at the beginning of this lecture. All right. So this is going to be the product of the two integrals. Okay. For x variable, we have limits from 0 to 1. For y variable, we have limits from 0 to 6. And here I'm doing these computations. So the integral from 0 to 1 of the function 1 over x plus 1 dx, that is the natural log of absolute value of x plus 1. And we carefully evaluate this expression, and natural log of 1, we know that's 0, so that's gone. So that's the answer for the first integral. Okay, so that's done. The second one is basically the same, right? So we have natural log of absolute value y plus 1. Plug in 0 and 6. Okay, so we get this expression. Again, natural log of 0. Natural log of 1 is 0. Okay, so the answer for the second integral is natural log of 7. So the final answer, we just multiply these two. Okay. All right, so we're going to stop right here. So you've seen a couple of things. So we've talked about Riemann sum for functions of two variables, what that looks like. Okay, so kind of discovered this notion of a double integral through double summation. Okay, and then we talked about some properties of double integrals and discussed 4 examples. Okay, so in the next lecture, we're going to talk about double integrals over regions that are no longer rectangular. Okay, and this is one of the reasons why I kind of emphasize the importance of the region of integrations is the rules will be slightly different. Okay, certain rules, not all of the rules. So that's why I'm going to continue and make pictures for regions of integrations when it's possible. All right. Okay, well, thank you all for watching, and I'll talk to you next time.